I'm Bo with FreeCodeCamp. This course from Fast AI will teach you practical deep learning. The main teacher is Jeremy Howard. He was president of the world's largest machine learning community, Kaggle, and he's been teaching machine learning for 30 years. Make sure to check the description for setup guides, code, and a free book that goes along with the course. So let's start.
So hello everybody and welcome to Deep Learning for Coders, Lesson 1. This is the fourth year that we've done this, but it's a very different and very special version for a number of reasons. The first reason it's different is because we are bringing it to you live from day number 1 of a complete shutdown, or not complete shutdown, but nearly complete shutdown of San Francisco. We're going to be recording it over the next 2 months in the midst of this global pandemic. So if things seem a little crazy sometimes in this course, I apologize, but that's why this is happening. The other reason it's special is because we're trying to make this our kind of definitive version, right? Since we've been doing this for a while now, we've actually finally gotten to the point where we almost feel like we know what we're talking about. To the point that Sylvain and I have actually written a book, and we've actually written a piece of software from scratch called the FastAI Library version 2. We've written a peer-reviewed paper about this library. So this is kind of designed to be like the version of the course that is hopefully going to last a while. The syllabus is based very closely on this book, right? So if you want to read along properly as you go, please buy it. And I say please buy it because actually the whole thing is also available for free in the form of Jupyter Notebooks. And that is thanks to the huge generosity of O'Reilly Media, who have let us do that. You'll be able to see on the website for the course how to kind of access all this. But here is the fast book repo where you can read the whole damn thing. At the moment, as you see, it's a draft, but by the time you see this, it won't be. So we have a big request here, which is the deal is this. You can read this thing for free as Jupyter Notebooks, but that is not as convenient as reading it on a Kindle or, you know, in a paper book or whatever. So please don't turn this into a PDF, right? Please don't turn it into a form designed more for reading, because kind of the whole point is that we hope, you know, that you'll buy it, right? Don't take advantage of O'Reilly's generosity by creating the thing that you know they're not giving you for free. And that's actually explicitly the license under which we're providing this as well. So there's a, you know, it's mainly a request to being a decent human being. If you see somebody else not being a decent human being and stealing the book version of the book, please tell them, please don't do that. It's not nice. And don't be that person. So either way, you can read along with the syllabus in the book. There's a couple of different versions of these notebooks, right? There's the full notebook that has the entire prose, pictures, everything. Now we actually wrote a system to turn notebooks into a printed book. And sometimes that looks kind of weird. For example, here's a weird looking table. And if you look in the actual book, it actually looks like a proper table, right? So sometimes you'll see like little weird bits. Okay, they're not mistakes, they're bits where we kind of add information to help our book turn into a proper nice book. So just ignore them. Now, when I say we, who is we? Well, I mentioned one important part of the we is Sylvain. Sylvain is my co-author of the book, and the FastAI version 2 library. So he is my partner in crime here. The other key we here is Rachel Thomas. And so maybe, Rachel, you can come and say hello. She's the co-founder of FastAI.
Hello. Yes, I'm the co-founder of FastAI. I'm also lower. Sorry, I'm taller than Jeremy. And I'm the founding director of the Center for Applied Data Ethics at the University of San Francisco. I'm really excited to be a part of this course, and I'll be the voice you hear asking questions from the forums.
Rachel and Sylvain are also the people in this group who actually understand math. I am a mere philosophy graduate. Rachel has a PhD. Sylvain has written 10 books about math. So if math questions come along, it's possible I may pass them along. But it's very nice to have an opportunity to work with people who understand this topic so well. Yes, Rachel. Did you want to? Sure. Oh, thank you. And as Rachel mentioned, the other area where she's, has real world-class expertise is data ethics. She is the founding director of the Center for Applied Data Ethics.
At the University of San Francisco.
At the University of San Francisco, thank you. We're going to be talking about data ethics throughout the course because, well, we happen to think it's very important. So for those parts, although I'll generally be presenting them, they will be on the whole based on Rachel's work, because she actually knows what she's talking about. Although thanks to her, I kind of know a bit about what I'm talking about too. Right, so that's that. Should you be here, is there any point you attempting to understand, let me press the right button, understand deep learning? Okay, so what do you should you be here? Is there any point you attempting to learn deep learning, or are you too stupid, or you don't have enough vast resources or whatever? Because that's what a lot of people are telling us. They're saying you need teams of PhDs and massive data centers full of GPUs, otherwise it's pointless. Don't worry, that is not at all true. It couldn't be further from the truth. In fact, the vast majority, so a lot of world-class research and world-class industry projects have come out of FastAI alumni and FastAI library-based projects and elsewhere, which are created on a single GPU using a few dozen or a few hundred data points from people that have no graduate level technical expertise, or in my case, I have no undergraduate level technical expertise. I'm just a philosophy major. So there is, and we'll see it throughout the course, but there is lots and lots and lots of clear empirical evidence that you don't need lots of math, you don't need lots of data, you don't need lots of expensive computers to do great stuff with deep learning. So just bear with us, you'll be fine. To do this course, you do need to code. Preferably, you know how to code in Python, but if you've done other languages, you can learn Python. If the only languages you've done is something like MATLAB, where you've used it more of kind of like a scripty kind of thing, you might find it a bit, you will find it a bit heavier going. But that's okay. Stick with it. You can learn Python as you go. Is there any point learning deep learning? Is it any good at stuff? If you are hoping to build a brain that is an AGI, I cannot promise we're going to help you with that.
And AGI stands for Artificial General Intelligence.
Thank you. What I can tell you, though, is that in all of these areas, deep learning is the best known approach to at least many versions of all of these things. So it is not speculative at this point whether this is a useful tool. It's a useful tool in lots and lots and lots of places. Extremely useful tool. And in many of these cases, it is equivalent to or better than human performance, at least according to some particular kind of narrow definition of things that humans do in these kinds of areas. So deep learning is pretty amazing, and if you kind of want to pause the video here and have a look through and try and pick some things out that you think might look interesting, then type that keyword and deep learning into Google and you'll find lots of papers and examples and stuff like that. Deep learning comes from a background of neural networks. As you'll see, deep learning is just a type of neural network learning. A deep one. We'll describe exactly what that means later. And neural networks are certainly not a new thing. They go back at least to 1943 when McCulloch and Pitts created a mathematical model of an artificial neuron and got very excited about where that could get to. And then in the 50s, Frank Rosenblatt then built on top of that he basically created some subtle changes to that mathematical model. And he thought that with these subtle changes, we could witness the birth of a machine that is capable of perceiving, recognizing, and identifying its surroundings without any human training or control. And he oversaw the building of this extraordinary thing, the Mark I perceptron at Cornell. So that was, I think this picture was 1961. Thankfully, nowadays, we don't have to build neural networks by running the damn wires from neuron to neuron, artificial neuron to artificial neuron. But you can kind of see the idea, a lot of connections going on. And you'll hear the word connection a lot in this course because that's what it's all about. Then we had the first AI winter, as it was known, which really, to a strong degree, happened because an MIT professor named Marvin Minsky and Tappert wrote a book called Perceptrons about Rosenblatt's invention, in which they pointed out that a single layer of these artificial neuron devices actually couldn't learn some critical things. It was like impossible for them to learn something as simple as the Boolean XOR operator. In the same book, they showed that using multiple layers of the devices actually would fix the problem. People didn't notice that part of the book and only noticed the limitation, and people basically decided that neural networks were going to go nowhere, and they kind of largely disappeared for decades. Until, in some ways, 1986. A lot happened in the meantime, but there was a big thing in 1986, which was MIT released a thing called a book, a series of 2 volumes of a book called Parallel Distributed Processing, in which they described this thing they call parallel distributed processing, where you have a bunch of processing units that have some state of activation and some output function and some pattern of connectivity and some propagation rule and some activation rule and some learning rule operating in an environment. And then they described how things that met these requirements could, in theory, do all kinds of amazing work. And this was the result of many, many researchers working together. There's a whole group involved in this project, which resulted in this very, very important book. And so the interesting thing here to me is that if you, as you go through this course, come back and have a look at this picture, and you'll see we are doing exactly these things. Everything we're learning about really is how do you do each of these 8 things. Right? And it's interesting that they include the environment, because that's something which very often data scientists ignore, which is you build a model, you've trained it, it's learned something, but what's the context it works in? And we'll be talking about that quite a bit over the next couple of lessons as well. So in the 80s, during and after this was released, people started building in this second layer of neurons, avoiding Minsky's problem. And in fact, it was shown that it was mathematically provable that by adding that one extra layer of neurons, it was enough to allow any mathematical model to be approximated to any level of accuracy with these neural networks. And so that was like the exact opposite of the Minsky thing. That was like, hey, there's nothing we can't do. Provably there's nothing we can't do. And so that was kind of when I started getting involved in neural networks. So I was a little bit later. I guess I was getting involved in the early 90s, and they were very widely used in industry. I was using them for very boring things like targeted marketing for retail banks. It tended to be big companies with lots of money that were using them. And it certainly, though, was true that often the networks were too big or slow to be useful. They were certainly useful for some things, but they never felt to me like they were living up to the promise for some reason. Now, what I didn't know, and nobody I personally met knew, was that actually there were researchers that had showed 30 years ago that to get practical good performance, you need more layers of neurons. Even though mathematically, theoretically, you can get as accurate as you want with just one extra layer, to do it with good performance, you need more layers. So when you add more layers to a neural network, you get deep learning. So deep doesn't mean anything like mystical. It just means more layers. More layers than just adding the one extra one. So thanks to that, neural nets are now living up to their potential, as we saw in that what's deep learning good at thing. So we could now say that Rosenblatt was right. We have a machine that's capable of perceiving, recognizing, and identifying its surroundings without any human training or control. That's definitely true. I don't think there's anything controversial about that statement based on the current technology. So we're going to be learning how to do that. We're going to be learning how to do that in exactly the opposite way of probably all of the other math and technical education you've had. We are not going to start with a 2-hour lesson about the sigmoid function, or a study of linear algebra, or a refresher course on calculus. And the reason for that is that people who study how to teach and learn have found that is not the right way to do it for most people. For most people, so we work a lot based on the work of Professor David Perkins from Harvard and others who work at similar things, who talk about this idea of playing the whole game. And so playing the whole game is it's based on the sports analogy. If you're going to teach somebody baseball, you don't take them out, into a classroom and start teaching them about the physics of a parabola and how to stitch a ball and a 3-part history of 100 years of baseball politics. And then, 10 years later, you let them watch a game. And then 20 years later, you let them play a game. Which is kind of like how math education is being done, right? Instead, with baseball, step 1 is to say, hey, let's go and watch some baseball. What do you think? That was fun, right? See that guy there? He's trying to run there before the other guy throws the ball over there. Hey, you want to try having a hit? Okay, so you're going to hit the ball, and then I have to try and catch it, and then you have to run over there. And so from step 1, you are playing the whole game.
Yeah, and just to add to that, when people start, they often may not have a full team or be playing a full 9 innings, but they still have a sense of what the game is and kind of the big picture idea.
Yeah. So there's lots and lots of reasons that this helps most human beings. Not everybody, right? There's a small percentage of people who like to build things up from the foundations and the principles. And not surprisingly, they are massively overrepresented in a university setting because the people who get to be academics are the people who thrive with the kind of, to me, upside down way that things are taught. But outside of universities, most people learn best in this top-down way, where you start with the full context. So step number 2 in these 7 principles, I'm only going to mention the first 3, is to make the game worth playing, which is like if you're playing baseball, you have a competition. You score. You try and win. You bring together teams from around the community and have people try to beat each other, and you have leaderboards of who's got the highest number of runs or whatever, right? So this is all about making sure that the thing you're doing, you're doing it properly. You're making it the whole thing. You're providing the context and the interest. So for the fast AI approach to to learning deep learning, what this means is that today we're going to train models end to end. We're going to actually train models, right? And they won't just be crappy models. They will be state-of-the-art, world-class models from today. And we're going to try to have you build your own state-of-the-art, world-class models from either today or next lesson, depending on how things go. And then number 3 in the 7 principles from Harvard is work on the hard parts, which is kind of like this idea of practice. Yes.
Oh, as I say, deliberate practice.
Yeah, deliberate practice, right? Work on the hard parts means that you don't just, swing a bat, at a ball every time, you go out and just muck around, but you train properly. You find the bit that you're the least good at. You figure out where the problems are. You work damn hard at it, right? So in the deep learning context, that means that we do not dumb things down, right? By the end of the course, you will have done the calculus. You will have done the linear algebra. You will have done the software engineering of the code, right? You will be practicing these things which are hard. So it requires tenacity and commitment, but hopefully you'll understand why it matters, because before you start practicing something, you'll know why you need that thing, because you'll be using it. Like, to make your model better, you'll have to understand that concept first. So for those of you used to a traditional university environment, this is going to feel pretty weird. And a lot of people say that they regret after a year of studying fast AI that they spent too much time studying theory and not enough time training models and writing code. That's the kind of like the number one piece of feedback we get of people who say, I wish I'd done things differently. It's that. So please try to, as best as you can, since you're here, follow along with this approach. We are going to be using a kind of a software stack. Sorry, Rachel, yes.
I just wanted to say one more thing about the approach. I think since so many of us spent so many years kind of with a traditional educational approach of bottom up, that this can feel very uncomfortable at first. I still feel uncomfortable with it sometimes, even though I'm committed to the idea. And that some of it is also kind of having to catch yourself and be okay with the not knowing the details, which I think can feel very unfamiliar or even wrong when you're kind of new to that, of like, oh wait, I'm using something and I don't understand every underlying detail. But you kind of have to trust that we're going to get to those details later.
So I can't empathize because I did not spend lots of time doing that, but I will tell you this. Teaching this way is very, very, very hard. I very often find myself jumping back into a foundations first approach because it's just so easy to be like, oh, you need to know this, you need to know this, you need to do this, and then you can know this. That's so much easier to teach. So I do find this much, much more challenging to teach, but hopefully it's worth it. We've spent a long, long time figuring out how to get deep learning into this format. But one of the things that helps us here is the software we have available. If you haven't used Python before, it's a ridiculously flexible and expressive and easy to use language. We have plenty of bits about it we don't love, but on the whole, we love the overall thing. And we think most importantly, the vast, vast, vast majority of deep learning practitioners and researchers are using Python. On top of Python, there are 2 libraries that most folks are using today, PyTorch and TensorFlow. There's been a very rapid change here. TensorFlow was what we were teaching until a couple of years ago. It's what everyone was using until a couple of years ago. It got super bogged down. Basically, TensorFlow got super bogged down. This other software called PyTorch came along that was much easier to use and much more, useful to researchers. Within the last 12 months, the percentage of papers at major conferences that uses PyTorch has gone from 20% to 80%, and vice versa. Those that use TensorFlow have gone from 80% to 20%. So basically all the folks that are actually building the technology we're all using are now using PyTorch. Industry moves a bit more slowly, but in the next year or two, you'll probably see a similar thing in industry. Now, the thing about PyTorch is it's super, super flexible and really is designed for flexibility and developer friendliness. It's certainly not designed for beginner friendliness. And it's not designed for what we would say, it doesn't have like higher level APIs, by which I mean there isn't really things to make it easy to build stuff quickly using PyTorch. To deal with that issue, we have a library called FastAI that sits on top of PyTorch. FastAI is the most popular higher level API for PyTorch. It is because our courses are so popular, some people are under the mistaken impression that FastAI is designed for beginners or for teaching. It is designed for beginners and teaching, as well as practitioners in industry and researchers. The way we do this makes sure that it's the best API for all of those people is we use something called a layered API. And so there's a peer-reviewed paper that Sylvain and I wrote that described how we did that. And for those of you that are software engineers, it will not be at all unusual or surprising. It's just totally standard software engineering practices, but they were practices that were not followed in any deep learning library we had seen. Basically lots of refactoring and decoupling. And so by using that approach, it's allowed us to build something which you can do super low-level research, you can do state-of-the-art production models, and you can do kind of super easy beginner world-class models. So that's the basic software stack. There's other pieces of software we'll be learning about along the way. But the main thing I think to mention here is it actually doesn't matter. If you learn this software stack and then at work you need to use TensorFlow and Keras, say, you'll be able to switch with, in less than a week. Lots and lots of students have done that. It's never been a problem. The important thing is to learn the concepts, right? And so we're going to focus on those concepts. And by using an API which minimizes the amount of boilerplate you have to use, it means you can focus on the bits that are important. The actual lines of code will correspond much more to the actual concepts you're implementing. You are going to need a GPU machine. A GPU is a graphics processing unit, and specifically you need an NVIDIA GPU. Other brands of GPU just aren't well supported by any deep learning libraries. Please don't buy one. Even if you already have one, you probably shouldn't use it. Instead, you should use one of the platforms that we have already got set up for you. It's just a huge distraction to be spending your time doing like system administration on a GPU machine and installing drivers and blah, 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 right? And run it on Linux, please. That's what everybody's doing, not just us. Everybody's running it on Linux. Like, make life easy for yourself. It's hard enough to learn deep learning without having to do it in a way that you're learning, all kinds of arcane hardware support issues. There's a lot of free options available, and so please use them. If you're using an option that's not free, don't forget to shut down your instance. So what's going to be happening is you're going to be spinning up a server that lives somewhere else in the world, and you're going to be connecting to it from your computer and training and running and building models. Just because you close your browser window doesn't mean your server stops running on the whole. Right? So don't forget to shut it down, because otherwise you're paying for it. Colab is a great system which is free. There's also a paid subscription version of it. Be careful with Colab. Most of the other systems we recommend save your work for you automatically, and you can come back to it any time. Colab doesn't. So be sure to check out the Colab platform thread on the forums to learn about that. So I mentioned the forums. The forums are really, really important because that is where all of the discussion and setup and everything happens. So for example, if you want help with setup, here, there's a setup help thread, and you can find out, how to best set up Colab, and you can see discussions about it, and you can ask questions. And please remember to search before you ask your question, right? Because it's probably been asked before, unless you're one of the very, very earliest people who are doing the course. So once you, step one is to get your server set up by just following the instructions from the forums or from the course website. And the course website will have lots of step-by-step instructions for each platform. They will vary in price, they will vary in speed, they will vary in availability, and so forth. Once you have finished following those instructions, the last step of those instructions will end up showing you something like this, the course v4 folder, so version 4 of our course. And by the time you see this video, this is likely to have more stuff in it, but it will have an NBs, standing for notebooks, folder. So you can click on that, and that will show you all of the notebooks for the course. What I want you to do is scroll to the bottom and find the one called App Jupyter, and click on that. And this is where you can start learning about Jupyter Notebook. What is Jupyter Notebook? Jupyter Notebook is something where you can start typing things and press Shift-Enter, and it will give you an answer. And so the thing you're typing is Python code, and the thing that comes out is the result of that code. And so you can put in anything in Python. X equals 3 times 4, x plus 1, and as you can see, it displays a result anytime there's a result to display. So for those of you that have done a bit of coding before, you will recognize this as a REPL, R-E-P-L, read, evaluate, print, loop. Most languages have some kind of REPL. The Jupyter Notebook REPL is particularly interesting because it has things like headings, graphical outputs, interactive, multimedia. It's a really astonishing piece of software. It's won some really big awards. It's I would have thought the most widely used REPL outside of shells like Bash. It's a very powerful system. We love it. We've written our whole book in it. We've written the entire FastAI library with it. We do all our teaching with it. It's extremely unfamiliar to people who have done most of their work in IDE. You should expect it to feel as awkward as perhaps the first time you moved from a GUI to a command line. It's different, right? So if you're not familiar with kind of REPL-based systems, it's going to feel super weird. But stick with it because it really is great. The model going on here is that this web page I'm looking at is letting me type in things for a server to do and show me the results of computations the server is doing. So the server is off somewhere else. It's not running on my computer, right? The only thing running on the computer is this web page. But as I do things, so for example, if I say x equals x times 3, this is updating the server's state. There's this state. There's like what's currently the value of x. And so I can find out now x is something different. So you can see when I did this line here, it didn't change the earlier x plus 1, right? So that means that when you look at a Jupyter Notebook, it's not showing you the current state of your server. It's just showing you what that state was at the time that you printed that thing out. It's just like if you use a shell like bash and you type ls and then you delete a file, that earlier ls you printed doesn't go back and change, right? That's kind of how REPLs generally work, including this one. Jupyter Notebook has two modes. One is edit mode, which is when I click on a cell and I get a flashing cursor and I can move left and right and type, right? There's not very many keyboard shortcuts in this mode. One useful one is Control or Command slash, which will comment and uncomment. The main one to know is Shift Enter to actually run the cell. At that point, there's no flashing cursor anymore, and that means that I'm now in command mode, not edit mode. So as I go up and down, I'm selecting different cells. So in command mode, as we move around, we're now selecting cells, and there are now lots of keyboard shortcuts you can use. So if you hit H, you can get a list of them, for example, and you'll see that they're not on the whole like control or command with something, they're just a letter on its own. So if you use like Vim, you'll be more familiar with this idea. So for example, if I hit C to copy and V to paste, then it copies the cell, or X to cut it, A to add a new cell above, and then I can press the various number keys to create a heading. So number 2 will create a heading level 2, and as you can see, I can actually type formatted text, not just code. The formatted text I type is in Markdown. Like so. My numbered one work. There you go. So that's in Markdown. If you haven't used Markdown before, it's a super useful way to write formatted text that is used very widely. So learn it because it's super handy, and you need it for Jupyter. So when you look at our book notebooks, for example, you can see an example of all the kinds of formatting and code and stuff here. So you should go ahead and go through the app Jupyter, and you can see here how you can create plots, for example, and create lists of things, and import libraries, and display pictures, and so forth. If you want to create a new notebook, you can just go new Python 3, and that creates a new notebook, which by default is just called Untitled, so you can then rename it to give it whatever name you like. And so then you'll now see that in the list here, new name. The other thing to know about Jupyter is that it's a nice, easy way to jump into a terminal if you know how to use a terminal. You certainly don't have to for this course, at least for the first bit. But if I go New Terminal, you can see here I have a terminal. One thing to note is for the notebooks are attached to a GitHub repository. If you haven't used GitHub before, that's fine. But basically, they're attached to a server where from time to time we will update the notebooks on that server. And you'll see on the course website and the forum, we tell you how to make sure you have the most recent versions. When you grab our most recent version, you don't want it to conflict with or overwrite your changes. So as you start experimenting, it's not a bad idea to like select a notebook and click duplicate, and then start doing your work in the copy. And that way, when you get an update of our latest course materials, it's not going to interfere with the experiments that you've been running. So there's two important repositories to know about. One is the Fastbook repository, which we saw earlier, which is kind of the the full book with all the outputs and prose and everything. And then the other one is the course v4 repository. And here is the exact same notebook from the course v4 repository. And for this one, we remove all of the prose and all of the pictures and all of the outputs and just leave behind the headings and the code. In this case, you can see some outputs because I just ran that code, but for most of it, there won't be any. Oh no, I guess we have left the outputs. I'm not sure if we'll keep that or not. So you may or may not see the outputs. So the idea with this is probably the version that you want to be experimenting with, because it kind of forces you to think about like what's going on as you do each step, you know, rather than just reading it and running it without thinking. We kind of want you to do it in this more bare environment in which you're thinking about like, oh, what did the book say? Why was this happening? And if you forget, then you can kind of go back to the book. The other thing to mention is both the Course v4 version and the Fastbook version at the end have a questionnaire. And quite a few folks have told us that, you know, amongst the reviewers and stuff, that they actually read the questionnaire first. We spent many, many weeks writing the questionnaires, Sylvain and I. And the reason for that is because we tried to think about like, what do we want you to take away from each notebook? So if you kind of read the questionnaire first, you can find out what are the things we think are important. What are the things that you should know before you move on? So rather than having like a summary section at the end saying, at the end of this, you should know blah, 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 we instead have a questionnaire to do the same thing. So please make sure you do the questionnaire before you move on to the next chapter. You don't have to get everything right. And most of the time answering the questions is as simple as going back to that part of the notebook and reading the prose. But if you've missed something, like, do go back and read it, because we're assuming, these are the things we're assuming you know. So if you don't know these things before you move on, it could get frustrating. Having said that, if you get stuck after trying a couple of times, do move on to the next chapter. Do 2 or 3 more chapters and then come back. Maybe by the time you've done a couple more chapters, you know, you'll get some more perspective. We try to re-explain things multiple times in different ways. So yeah, it's okay if you've tried and you get stuck, then you can try moving on. All right, so let's try running the first part of the notebook. So here we are in O1 intro. So this is chapter 1, and here is our first cell. So I click on the cell, and by default, actually there will be a header and a toolbar. As you can see, you can turn them on and off. I always leave them off myself. And so to run this cell, you can either click on the play, you know, the run button, or as I mentioned, you can hit Shift Enter. So for this one, I'll just click. And as you can see, this star appears. So this says I'm running. And now you can see a progress bar popping up. That's going to take a few seconds. Okay? And so as it runs, it's going to print out some results. Don't expect to get exactly the same results as us. There's some randomness involved in training a model. And that's okay. Don't expect to get exactly the same time as us. If this first cell takes more than 5 minutes, unless you have a really old GPU, that's probably a bad sign. You might want to hop on the forums and figure out what's going wrong. Or maybe you're trying to use Windows, which really doesn't work very well for this at the moment. Don't worry that we don't know what all the code does yet. We're just making sure that we can train a model. So here we are. It's finished running. And so as you can see, it's printed out some information. And in this case, it's showing me that there's an error rate of 0.005 at doing something. What is the something it's doing? Well, what it's doing here is it's actually grabbing a data set we call the pets data set, which is a data set of pictures of cats and dogs, and it's trying to figure out which ones are cats and which ones are dogs. And as you can see, after about well less than a minute, it's able to do that with a 0.5% error rate. So it can do it pretty much perfectly. So we've trained our first model. We have no idea how, we don't know what we were doing, but we have indeed trained a model. So that's a good start. And as you can see, we can train models pretty quickly on a single computer, which, many of which you can get for free. One more thing to mention is if you have a Mac, it doesn't matter whether you have Windows or Mac or Linux in terms of what's running in the browser, but if you have a Mac, please don't try to use that GPU. Macs actually, Apple doesn't even support NVIDIA GPUs anymore, so that's really not going to be a great option. So stick with Linux. It'll make life much easier for you. Well, actually, the first thing we should do is actually try it out. So I claim we've trained a model that can pick cats from dogs. Let's make sure we can. So let's check out this cell. This is interesting, right? We've created a widgets.fileUpload object and displayed it, and this is actually showing us a clickable button. So as I mentioned, this is an unusual REPL. We can even create GUIs in this REPL. So if I click on this file upload, and I can pick cat, there we go, and I can now turn that uploaded data into an image. There's a cat, and now I can do predict, and it's a cat with a 99.96% probability. So we can see we have just uploaded an image that we've picked out. So you should try this, right? Grab a picture of a cat, find one from the internet, or go and take a picture of one yourself, and make sure that you get a picture of a cat. This is something which can recognize photos of cats, not line drawings of cats. And so as we'll see in this course, these kinds of models could only learn from the kinds of information you give it. And so far we've only given it, as you'll discover, photos of cats, not anime cats, not drawn cats, not abstract representations of cats, but just photos. So we're now going to look at what's actually happened here. And you'll see at the moment I'm not getting some great information here. If you see this in your notebooks, you'll have to go File, Trust Notebook, and that just tells Jupyter that it's allowed to run the code necessary to display things to make sure that there isn't any security problems. And so you'll now see the outputs. Sometimes you'll actually see some weird code like this. This is code that actually creates outputs. Sometimes we hide that code, sometimes we show it. So generally speaking, you can just ignore the stuff like that and focus on what comes out. So I'm not going to go through these. Instead, I'm going to have a look at it. The same thing over here on the slides. So what we're doing here is we're doing machine learning. Deep learning is a kind of machine learning. What is machine learning? Machine learning is just like regular programming. It's a way to get computers to do something. But in this case, it's pretty hard to understand how you would use regular programming to recognize dog photos from cat photos. How do you kind of create the loops and the variable assignments and the conditionals to create a program that recognizes dogs versus cats in photos? It's super hard. Super hard. So hard that until kind of the deep learning era, nobody really had a model that was remotely accurate at this apparently easy task. Because we can't write down the steps necessary. So normally, we write down a function that takes some inputs and goes through our program and gives us some results. So this general idea where the program is something that we write the steps doesn't seem to work great for things like recognizing pictures. So back in 1949, somebody named Arthur Samuel started trying to figure out a way to solve problems like recognizing pictures of cats and dogs. And in 1962, he described a way of doing this. Well, first of all, he described the problem. Programming a computer for these kinds of computations is at best a difficult task because of the need to spell out every minute step of the process in exasperating detail. Computers are giant morons, which all of us coders totally recognize. So he said, okay, let's not tell the computer the exact steps, but let's give it examples of a problem to solve and figure out how to solve it itself. And so by 1961, he had built a checkers program that had beaten the Connecticut state champion, not by telling it the steps to take to play checkers, but instead by doing this, which is arrange for an automatic means of testing the effectiveness of a weight assignment in terms of actual performance, and a mechanism for altering the weight assignment so as to maximize performance. This sentence is the key thing, and it's a pretty tricky sentence, so we can spend some time on it. The basic idea is this. Instead of saying inputs to a program and then outputs, let's have inputs to a, let's call the program now model, but it's the same basic idea. Inputs to a model and results, and then we're going to have a second thing called weights. And so the basic idea is that this model is something that creates outputs based not only on, for example, the state of a checkers board, but also based on some set of weights or parameters that describe how that model is going to work. So the idea is, if we could like enumerate all the possible ways of playing checkers, and then kind of describe each of those ways using some set of parameters, or what Arthur Samuel called weights, then if we had a way of checking how effective a current weight assignment is in terms of actual performance, in other words, does that particular enumeration of a strategy for playing checkers end up winning or losing games, right? And then a way to alter the weight assignment so as to maximize the performance. So then, oh, let's try increasing or decreasing each one of those weights one at a time to find out if there's a slightly better way of playing checkers, and then do that lots of times. Then eventually, such a procedure could be made entirely automatic. And then the machine so programmed would learn from its experience. So this little paragraph is, it's the thing. This is machine learning, right? A way of creating programs such that they learn rather than they're programmed. So, if we had such a thing, then we would basically now have something that looks like this. You have inputs and weights again, going into a model, creating results, i.e. you won or you lost, and then a measurement of performance. So remember that was this key step, and then the second key step is a way to update the weights based on the measure of performance, and then you could loop through this process and train a machine learning model. So this is the abstract idea. So after we've run that for a while, right, it's come up with a set of weights that's pretty good, right? We can now forget the way it was trained, and we have something that's just like this, right? Except the word program is now replaced with the word model. So a trained model can be used just like any other computer program. So the idea is we're building a computer program not by putting out the steps necessary to do the task, but by training it to learn to do the task, at the end of which it's just another program. And so this is what's called inference, right? It's using a trained model as a program to do a task such as playing checkers. So machine learning is training programs developed by allowing a computer to learn from its experience rather than through manually coding. Okay, how would you do this for image recognition? What is that model and that set of weights such that as we vary them, it could get better and better at recognizing cats versus dogs? I mean, for checkers, it's not too hard to imagine how you could kind of enumerate, like, depending on different kinds of how far away the opponent's piece is from your piece, what should you do in that situation, how should you weight defensive versus aggressive strategies, blah, blah, blah. not at all obvious how you would do that for image recognition. So what we really want is some function in here which is so flexible that there's a set of weights that could cause it to do anything. Like the world's most flexible possible function. And it turns out that there is such a thing. It's a neural network. So we'll be describing exactly what that mathematical function is in the coming lessons. To use it, it actually doesn't really matter what the mathematical function is. It's a function which is, we say, parameterized by some set of weights, by which I mean as I give it a different set of weights, it does a different task. And it can actually do any possible task. Something called the universal approximation theorem tells us that mathematically provably, this functional form can solve any problem that is solvable to any level of accuracy if you just find the right set of weights. Which is kind of restating what we described earlier in that, like, oh, how do we deal with the Marvin-Minsky problem? So neural networks are so flexible that if you could find the right set of weights, they can solve any problem, including, is this a cat or is it a dog? So that means you need to focus your effort on the process of training them, that is, finding good weights, good weight assignments, to use Arthur Samuel's terminology. So how do you do that? We want a completely general way to do this, to update the weights based on some measure of performance, such as how good is it at recognizing cats versus dogs? And luckily, it turns out such a thing exists. And that thing is called stochastic gradient descent, or SGD. Again, we'll look at exactly how it works. We'll build it from ourselves from scratch, but for now, we don't have to worry about it. I will tell you this, though. Neither SGD nor neural nets are at all mathematically complex. They nearly entirely are addition and multiplication. The trick is it just does a lot of them, like billions of them, so many more than we can like intuitively grasp, but they can do extraordinarily powerful things. But they're not rocket science at all. They're not complex things. And we'll see exactly how they work. Right, so that's the Arthur Samuel version, right? Nowadays we don't use quite the same terminology, but we use exactly the same idea. So that function that sits in the middle we call an architecture. An architecture is the function that we're adjusting the weights to get it to do something. So that's the architecture. That's the functional form of the model. Sometimes people say model to mean architecture, so don't let that confuse you too much, but really the right word is architecture. We don't call them weights, we call them parameters. Weights has a specific meaning, it's quite a particular kind of parameter. The things that come out of the model, the architecture with the parameters, we call them predictions. And the predictions are based on two kinds of inputs. Independent variables, that's the data, like the pictures of the cats and the dogs. And dependent variables, also known as labels, which is like the thing saying, this is a cat, this is a dog, this is a cat. So that's your inputs. So the results are predictions. The measure of performance, to use Arthur Samuel's word, is known as the loss. So the loss is being calculated from the labels and the predictions. Okay, and then there's the update back to the parameters. Okay, so this is the same picture as we saw, but just putting in the words that we use today. So this picture, if you forget, if I say these are the parameters of this, used for this architecture to create a model, you can go back and remind yourself, what did I mean? What are the parameters? What are the predictions? What is the loss? Okay, the loss is some function that measures the performance of the model in such a way that we can update the parameters. So, it's important to note that deep learning and machine learning are not magic, right? The model can only be created where you have data showing you examples of the thing that you're trying to learn about. It can only learn to operate on the patterns that you've seen in the input used to train it, right? So if we don't have any line drawings of cats and dogs, then there's never going to be an update to the parameters that makes the architecture, and so the architecture and the parameters together is the model, so we'll just say the model, that makes the model better at predicting line drawings of cats and dogs, because they never received those weight updates because they'd never received those inputs. Notice also that this learning approach only ever creates predictions. It doesn't tell you what to do about it. And that's going to be very important when we think about things like a recommendation system of like, what product do we recommend to somebody? Well, I don't know. We don't do that, right? We can predict what somebody will say about a product after we've shown them, but we're not creating actions. We're creating predictions. And that's a super important difference to recognize. It's not enough just to have examples of input data like pictures of dogs and cats. We can't do anything without labels. And so very often organizations say we don't have enough data. Most of the time they mean we don't have enough labeled data. Because if a company is trying to do something with deep learning, often it's because they're trying to automate or improve something they're already doing, which means by definition they have data about that thing or a way to capture data about that thing because they're doing it, right? But often the tricky part is labeling it. So for example, in medicine, if you're trying to build a model for radiology, you can almost certainly get lots of medical images about just about anything you can think of, but it might be very hard to label them according to malignancy of a tumor or according to whether or not meningioma is present or whatever, because these kinds of labels are not necessarily captured in a structured way, at least in the US medical system. So that's an important distinction that really impacts your kind of strategy here. So then a model, as we saw from the PDP book, a model operates in an environment, right? You roll it out and you do something with it. And so then this piece of that kind of PDP framework is super important, right? You have a model that's actually doing something. For example, you've built a predictive policing model that predicts, doesn't recommend actions, it predicts where an arrest might be made. This is something a lot of jurisdictions in the US are using. Now, it's predicting that based on data and based on labeled data. And in this case, it's actually going to be using, in the US, for example, data where I think depending on whether you're black or white, black people in the US, I think, get arrested something like 7 times more often for, say, marijuana possession than whites, even though the actual underlying amount of marijuana use is about the same in the two populations. So if you start with biased data and you build a predictive policing model, its prediction will say, oh, you will find somebody you can arrest here based on some biased data. So then law enforcement officers might decide to focus their police activity on the areas where those predictions are happening, as a result of which they'll find more people to arrest. And then they'll use that to put it back into the model, which will now find, oh, there's even more people we should be arresting in the black neighborhoods, and thus it continues. So this would be an example of a modeling interacting with its environment to create something called a positive feedback loop, where the more a model is used, the more biased the data becomes, making the model even more biased, and so forth. So one of the things to be super careful about with machine learning is recognizing how that model is actually being used and what kinds of things might happen as a result of that.
I was just going to add that this is also an example of proxies, because here arrest is being used as a proxy for crime. And I think that pretty much in all cases, the data that you actually have is a proxy for some value that you truly care about. And that difference between the proxy and the actual value often ends up being significant.
Thanks, Rachel. That's a really important point. Okay, so let's finish off by looking at what's going on with this code. So the code we ran is basically 1, 2, 3, 4, 5, 6 lines of code. So the first line of code is an import line. So in Python, you can't use an external library until you import from it. Normally in Python, people import just the functions and classes that they need from a library. But Python does provide a convenient facility where you can import everything from a module, which is by putting a star there. Most of the time, this is a bad idea, because by default, the way Python works is that if you say import star, it doesn't only import the things that are interesting and important in the library you're trying to get something from, but it also imports things from all the libraries it used and all the libraries they used, and you end up kind of exploding your namespace in horrible ways and causing all kinds of bugs. Because FastAI is designed to be used in this REPL environment where you want to be able to do a lot of quick, rapid prototyping, we actually spent a lot of time figuring out how to avoid that problem so that you can import star safely. So whether you do this or not is entirely up to you, but rest assured that if you import star from a FastAI library, it's actually been explicitly designed in a way that you only get the bits that you actually need. One thing to mention is in the video you see it's called FastAI 2. That's because we're recording this video using a pre-release version. By the time you're watching the online, the MOOC version of this, you will have the 2 will be gone. Something else to mention is there are, as I speak, 4 main predefined applications in FastAI, being vision, text, tabular, and collaborative filtering. We'll be learning about all of them and a lot more. For each one, say here's vision, you can import from the .all kind of meta module, I guess we could call it, and that will give you all the stuff that you need for most common vision applications. So if you're using a REPL system like Jupyter Notebook, it's going to give you all the stuff right there that you need without having to go back and figure it out. One of the issues with this is a lot of Python users don't, if they look at something like untar data, they would figure out where it comes from by looking at the import line. And so if you import star, you can't do that anymore. But the good news is, in a REPL, you don't have to. You can literally just type the symbol, press Shift-Enter, and it will tell you exactly where it came from, as you can see. So that's super handy. So in this case, for example, to do the actual building the data set, we called image data loaders from namefunc. And I can actually call this special doc function to get the documentation for that. And as you can see, it tells me exactly everything to pass in, what all the defaults are, and most importantly, not only what it does, but show in docs pops me over to the full documentation, including an example. Everything in the FastAI documentation has an example, and the cool thing is the entire documentation is written in Jupyter Notebooks. So that means you can actually open the Jupyter Notebook for this documentation and run the line of code yourself and see it actually working and look at the outputs and so forth. Also in the documentation, you will find there's a bunch of tutorials. So for example, if you look at the vision tutorial, it'll cover lots of things, but one of the things it'll cover is, as you can see in this case, pretty much the same kind of stuff we're actually looking at in lesson 1. So there's a lot of documentation in FastAI, and taking advantage of it is a very good idea, and it is fully searchable. And as I mentioned, perhaps most importantly, that every one of these documentation pages is also a fully interactive Jupyter Notebook. So looking through more of this code, the first line after the import is something that uses untar data. That will download a data set, decompress it, and put it on your computer. If it's already downloaded, it won't download it again. If it's already decompressed, it won't decompress it again. And as you can see, FastAI already has predefined access to a number of really useful data sets, such as this PETS data set. Data sets are a super important part, as you can imagine, of deep learning. We'll be seeing lots of them, and these are created by lots of heroes who basically spend months or years collating data that we can use to build these models. The next step is to tell FastAI what this data is, and we'll be learning a lot about that. But in this case, we're basically saying, okay, it contains images. It contains images that are in this path. So untarred data returns the path that is whereabouts it's been decompressed to. Or if it's already decompressed, it tells us where it was previously decompressed to. We have to tell it things like, okay, what images are actually in that path? One of the really interesting ones is label function. How do you tell for each file whether it's a cat or a dog? And if you actually look at the README for the original data set, it uses a slightly quirky thing, which is they said, oh, anything where the first letter of the file name is an uppercase is a cat. That's what they decided. So we just created a little function here called isCat that returns the first letter, is it uppercase or not? And we tell FastAI that's how you tell if it's a cat. We'll come back to these two in a moment. So the next thing, so now we've told it what the data is. We then have to create something called a learner. A learner is a thing that learns. It does the training. So you have to tell it what data to use. Then you have to tell it what architecture to use. We'll be talking a lot about this in the course, but basically there's a lot of predefined neural network architectures that have certain pros and cons. And for computer vision, the architecture is called ResNet. Just a super great starting point, and so we're just going to use a reasonably small one of them. So these are all predefined and set up for you. And then you can tell FastAI what things you want to print out as it's training. In this case, we're saying, oh, tell us the error, please, as you train. So then we can call this really important method called fine-tune that we'll be learning about in the next lesson, which actually does the training. Valid% does something very important. It grabs, in this case, 20% of the data, 0.2 proportion, and does not use it for training a model. Instead, it uses for telling you the error rate of the model. So always in FastAI, this metric, the error rate, will always be calculated on a part of the data which has not been trained with. And the idea here, and we'll talk a lot more about this in the future lessons, but the basic idea here is we want to make sure that we're not overfitting. Let me explain. Overfitting looks like this. Let's say you're trying to create a function that fits all these dots, right? A nice function would look like that, right? But you could also actually fit it much more precisely with this function. Look, this is going much closer to all the dots than this one is, right? So this is obviously a better function, except as soon as you get outside where the dots are, especially if you go off the edges, it's obviously doesn't make any sense. So this is what you would call an overfit function. So overfitting happens for all kinds of reasons. We use a model that's too big, or we use not enough data. We'll be talking all about it, right? But really, the craft of deep learning is all about creating a model that has a proper fit. And the only way you know if a model has a proper fit is by seeing whether it works well on data that was not used to train it. And so we always set aside some of the data to create something called a validation set. So the validation set is the data that we use not to touch it at all when we're training a model, but we're only using it to figure out whether the model's actually working or not. One thing that Sylvain mentioned in the book is that one of the interesting things about studying FastAI is you learn a lot of interesting programming practices. So I've been programming, since I was a kid, so like 40 years. And Sylvain and I both work really, really hard to make Python do a lot of work for us and to use, programming practices which make us very productive and allow us to come back to our code years later and still understand it. And so you'll see in our code, we'll often do things that you might not have seen before. And so a lot of students who have gone through previous courses say they learned a lot about coding and Python coding and software engineering from the course. So yeah, check, when you see something new, check it out and feel free to ask on the forums if you're curious about why something was done that way. One thing to mention is, just like they mentioned, like import star is something most Python programmers don't do because most libraries don't support doing it properly. We do a lot of things like that. We do a lot of things where we don't follow a traditional approach to Python programming. Because I've used so many languages over the years, I code not in a way that's specifically Pythonic, but incorporates like ideas from lots of other languages and lots of other notations, and heavily customize our approach to Python programming based on what works well for data science. That means that the code you see in FastAI is probably not going to fit with the kind of style guides and normal approaches at your workplace if you use Python there. So obviously, you should make sure that you fit in with your organization's programming practices rather than following ours. But perhaps in your own hobby work, you can follow ours and see if you find that interesting and helpful, or even experiment with that in your company if you're a manager and you're interested in doing so. Okay, so to finish, I'm going to show you something pretty interesting, which is, have a look at this code. Untar data, image data loaders from namefunc, learner, fine tune. Untar data, segmentation data loaders from labelfunc, learner, fine tune. Almost the same code, and this has built a model that does something, whoa, totally different. It's something which has taken images. This is on the left. This is the labeled data. It's got images with color codes to tell you whether it's a car or a tree or a building or a sky or a line marking or a road. And on the right is our model. And our model has successfully figured out for each pixel, is that a car, a line marking, a road? Now it's only done it in under 20 seconds, right? So it's a very small, quick model. So it's made some mistakes, like it's missing this line marking and some of these cars it thinks is house, right? But you can see, so if you train this for a few minutes, it's nearly perfect. But you can see the basic idea is that we can very rapidly, with almost exactly the same code, create something not that classifies cats and dogs, but does what's called segmentation. Figures out what every pixel in an image is. Look, here's the same thing. From import star, text loaders from folder, learner, learn fine tune. Same basic code. This is now something where we can give it a sentence and it can figure out whether that is expressing a positive or negative sentiment. And this is actually giving a 93% accuracy on that task in about 15 minutes on the IMDb dataset, which contains thousands of full-length movie reviews, like 1,000 to 3,000 word movie reviews. And this number here that we got with the same 3 lines of code would have been the best in the world for this task in a very, very, very popular academics dataset in like 2015, I think. So we are creating world-class models in our browser using the same basic code. Here's the same basic steps again from import star, untart data, tabular data loaders from CSV, learner, fit. This is now building a model that is predicting, let's find out, salary based on a CSV table containing these columns. So this is tabular data. Here's the same basic steps from import star, untart data, collab data loaders from CSV, learner, learn fine tune. This is now building something which predicts for each combination of a user and a movie what rating do we think that user will give that movie based on what other movies they've watched and liked in the past. This is called collaborative filtering and used in recommendation systems. So here you've seen some examples of each of the 4 applications in FastAI. And as you'll see throughout this course, the same basic code and also the same basic mathematical and software engineering concepts allow us to do vastly different things using the same basic approach. And the reason why is because of Arthur Samuel. It's because of this basic description of what it is you can do if only you have a way to parameterize a model and you have an update procedure which can update the weights to make you better at your loss function. And in this case, we can use neural networks, which are totally flexible functions. So that's it for this first lesson. It's a little bit shorter than other lessons are going to be. And the reason for that is that we are, as I mentioned, at the start of a global pandemic here, or at least in the West. In other countries, they are much further into it. So we spent some time talking about that at the start of the course, and you can find that video elsewhere. So in future lessons, there will be more time on deep learning. So what I suggest you do over the next week before you work on the next lesson is just make sure that you can spin up a GPU server, that you can shut it down when it's finished, that you can run all of the code here. And as you go through it, see, is this using Python in a way you recognize? Use the documentation, use that doc function, do some searching of the FastAI doc, see what it does, see if you can actually grab the FastAI documentation notebooks themselves and run them. Just try to get comfortable, that you kind of can know your way around. Because the most important thing to do with this style of learning, this top-down learning, is to be able to run experiments. And that means you need to be able to run code. So my recommendation is don't move on until you can run the code. Read the chapter of the book. And then go through the questionnaire. We've still got some more work, some more stuff to do about validation sets and test sets and transfer learning, so you won't be able to do all of it yet, but try to do all the parts that you can based on what we've seen in the course so far. Rachel, anything you wanted to add before we go? Okay, so thanks very much for joining us for lesson 1, everybody, and really looking forward to seeing you next time, where we will learn about transfer learning, and then we will move on to creating a actual production version of an application that we can actually put out on the internet, and you can start building apps that you can show your friends and they can start playing with. All right, bye everybody. So hello everybody, and welcome back to Practical Deep Learning for Coders. This is lesson 2, and in the last lesson we started training our first models. We didn't really have any idea how that training was really working, but we were looking at a high level at what was going on, and we learned about what is machine learning and how does that work. And we realized that based on how machine learning worked, that there are some fundamental limitations on what it can do. And we talked about some of those limitations. And we also talked about how after you've trained a machine learning model, you end up with a program which behaves much like a normal program. It's something with inputs and a thing in the middle and outputs. So today we're going to finish up talking about that, and we're going to then look at how we get those models into production and what some of the issues with doing that might be. I wanted to remind you that there are two sets of notebooks available to you. One is the Fastbook repo, the full actual notebooks containing all the text of the O'Reilly book. And so this lets you see everything that I'm telling you in much more detail. And then as well as that, there's the course V4 repo, which contains exactly the same notebooks, but with all the prose stripped away to help you study. So that's where you really want to be doing your experiment and your practice. And so maybe as you listen to the video, you can kind of switch back and forth between the video and reading, or do one and then the other, and then put it away and have a look at the Course V4 notebooks and try to remember, like, okay, what was this section about, and run the code and see what happens and change it and so forth. So we were looking at this line of code where we looked at how we created our data by passing in information, perhaps most importantly, some way to label the data. And we talked about the importance of labeling. And in this case, this particular data set, whether it's a cat or a dog, you can tell by whether it's an uppercase or a lowercase letter in the first position. That's just how this data set, they tell you in the README, works. And we also looked particularly at this idea of valid % equals 0.2, and like, what does that mean? It creates a validation set. And that was something I wanted to talk more about. The first thing I want to do though is point out that this particular labeling function returns something that's either true or false. And actually this data set, as we'll see later, also contains the actual breed of 37 different cat and dog breeds. So you can also grab that from the file name. In each of those two cases, we're trying to predict a category. Is it a cat or is it a dog? Or is it a German Shepherd or a Beagle or a Ragdoll cat or whatever? When you're trying to predict a category, so when the label is a category, we call that a classification model. On the other hand, you might try to predict how old is the animal, or how tall is it, or something like that, which is like a continuous number that could be like 13.2 or 26.5 or whatever. Anytime you're trying to predict a number, your label is a number, you call that regression. Okay, so those are the two main types of model: classification and regressions. This is very important jargon to know about. So a regression model attempts to predict one or more numeric quantities such as temperature or location or whatever. This is a bit confusing because sometimes people use the word regression as a shortcut to a abbreviation for a particular kind of model called linear regression. That's super confusing because that's not what regression means. Linear regression is just a particular kind of regression. But I just wanted to warn you of that. When you start talking about regression, a lot of people will assume you're talking about linear regression, even though that's not what the word means. All right, so I wanted to talk about this valid % 0.2 thing. So as we described, valid % grabs, in this case, 20% of the data, if it's 0.2, and puts it aside, like in a separate bucket. And then when you train your model doesn't get to look at that data at all. That data is only used to decide, to show you how accurate your model is. So if you train for too long, and or with not enough data, and or a model with too many parameters, after a while the accuracy of your model will actually get worse. And this is called overfitting, right? So we use the validation set to ensure that we're not overfitting. The next line of code that we looked at is this one, where we created something called a learner. We'll be learning a lot more about that, but a learner is basically, or is, something which contains your data and your architecture. That is the mathematical function that you're optimizing. And so a learner is the thing that tries to figure out what are the parameters which best cause this function to match the labels in this data. So we'll be talking a lot more about that, but basically this particular function, ResNet34, is the name of a particular architecture, which is just very good for computer vision problems. In fact, the name really is ResNet, and then 34 tells you how many layers there are. So you can use ones with bigger numbers here to get more parameters that will take longer to train, take more memory, more likely to overfit, but could also create more complex models. Right now, though, I wanted to focus on this part here, which is metrics equals error rate. This is where you list the functions that you want to be called with your data, with your validation data, and printed out after each epoch. An epoch is what we call it when you look at every single image in the data set once. And so after you've looked at every image in the data set once, we print out some information about how you're doing. And the most important thing we print out is the result of calling these metrics. So error rate is the name of a metric, and it's a function that just prints out what % of the validation set are being incorrectly classified by your model. So a metric's a function that measures the quality of the predictions using the validation set. So error rate's 1. Another common metric is accuracy, which is just 1 minus error rate. So very important to remember from last week, we talked about loss. Arthur Samuel had this important idea in machine learning that we need some way to figure out how well our model is doing, so that when we change the parameters, we can figure out which set of parameters make that performance measurement get better or worse. That performance measurement is called the loss. The loss is not necessarily the same as your metric. The reason why is a bit subtle, and we'll be seeing it in a lot of detail once we delve into the math in the coming lessons. But basically, you need a function. You need a loss function where if you change the parameters by just a little bit up or just a little bit down, you can see if the loss gets a little bit better or a little bit worse. And it turns out that error rate and accuracy doesn't tell you that at all, because you might change the parameters by such a small amount that none of your dog's predictions start becoming cats and none of your cat predictions start becoming dogs. So like your predictions don't change and your error rate doesn't change. So loss and metric are closely related, but the metric is the thing that you care about. The loss is the thing which your computer is using as the measurement of performance to decide how to update your parameters. So we measure overfitting by looking at the metrics on the validation set. So FastAI always uses the validation set to print out your metrics. And overfitting is like the key thing that machine learning is about. It's all about how do we find a model which fits the data, not just for the data that we're training with, but for data that the training algorithm hasn't seen before. So overfitting results when our model is basically cheating. Our model can cheat by saying, oh, I've seen this exact picture before, and I remember that that's a picture of a cat. So it might not have learnt what cats look like in general. It just remembers, that images 1, 4, and 8 are cats, and 2, and 3, and 5 are dogs, and learns nothing actually about what they really look like. So that's the kind of cheating that we're trying to avoid. We don't want it to memorize our particular data set. So we split off our validation data. And most of these words you're seeing on the screen are from the book. Okay, so I just copied and pasted them. So if we split off our validation data and make sure that our model sees it during training, it's completely untainted by it, so we can't possibly cheat. Not quite true. We can cheat. The way we could cheat is we could fit a model, look at the result in the validation set, change something a little bit, fit another model, look at the validation set, change something a little bit. And we could do that like 100 times until we find something where the validation set looks the best. But now we might have fit to the validation set, right? So if you want to be really rigorous about this, you should actually set aside a third bit of data called the test set that is not used for training and it's not used for your metrics. It's actually, you don't look at it until the whole project's finished. And this is what's used on competition platforms like Kaggle. On Kaggle, after the competition finishes, your performance will be measured against a data set that you have never seen. And so that's a really helpful approach, and it's actually a great idea to do that, like even if you're not doing the modeling yourself. So if you're looking at vendors and you're just trying to decide, should I go with IBM or Google or Microsoft, and they're all showing you how great their models are, what you should do is you should say, okay, you go and build your models, and I am going to hang on to 10% of my data, and I'm not going to let you see it at all. And when you're all finished, come back, and then I'll run your model on the 10% of data you've never seen. Now, pulling out your validation and test sets is a bit subtle though. Here's an example of a simple little data set. And this comes from a fantastic blog post that Rachel wrote that we will link to about creating effective validation sets. And you can see basically you have some kind of seasonal data set here. Now, if you just say, okay, FastAI, I want to model that. I want to create my data loader using a valid percent of 0.2. It would do this. It would delete randomly some of the dots, right? Now, this isn't very helpful because we can still cheat because these dots are right in the middle of other dots. And this isn't what would happen in practice. What would happen in practice is we would want to predict, this is sales by date, right? We want to predict the sales for next week, not the sales for 14 days ago, 18 days ago, and 29 days ago, right? So what you actually need to do to create an effective validation set here is not do it randomly, but instead chop off the end. Right? And so this is what happens in all Kaggle competitions pretty much that involve time, for instance, is the thing that you have to predict is the next like 2 weeks or so after the last data point that they give you. And this is what you should do also for your test set. So again, if you've got vendors that you're looking at, you should say to them, okay, after you're all done modeling, we're going to check your model against data that is 1 week later than you've ever seen before. And you won't be able to retrain or anything, because that's what happens in practice, right? Okay. So,
there's a question. Yeah. I've heard people describe overfitting as training error being below validation error. Does this rule of thumb end up being roughly the same as yours?
Okay, so that's a great question. So I think what they mean there is training loss versus validation loss, because we don't print training error. So we do print at the end of each epoch the value of your loss function for the training set and the value of the loss function for the validation set. And if you train for long enough, so if it's training nicely, your training loss will go down and your validation loss will go down. Because by definition, loss function is defined such as a lower loss function is a better model. If you start overfitting, your training loss will keep going down, right? Because like, why wouldn't it? You know, you're getting better and better parameters. But your validation loss will start to go up because actually you've started fitting to the specific data points in the training set. And so it's not going to actually get better. It's not going to get better for the validation set. It'll start to get worse. However, that does not necessarily mean that you're overfitting, or at least not overfitting in a bad way. As we'll see, it's actually possible to be at a point where the validation loss is getting worse, but the validation accuracy or error or metric is still improving. So I'm not going to describe how that would happen mathematically yet, because we need to learn more about loss functions, but we will. But for now, just realize that the important thing to look at is your metric getting worse, not your loss function getting worse. Thank you for that fantastic question. The next important thing we need to learn about is called transfer learning. So the next line of code said learn.finetune. Why does it say learn.finetune? Fine-tune is what we do when we are transfer learning. So transfer learning is using a pre-trained model for a task that is different to what it was originally trained for. So more jargon to understand our jargon. Let's look at that. What's a pre-trained model? So what happens is, remember I told you the architecture we're using is called ResNet34. So when we take that ResNet34, that's just it's just a mathematical function. Okay. with lots of parameters that we're going to fit using machine learning. There's a big data set called ImageNet that contains 1.3 million pictures of 1,000 different types of thing, whether it be mushrooms or animals or aeroplanes or hammers or whatever. There's a competition, or there used to be a competition that runs every year to see who could get the best accuracy on the ImageNet competition. And the models that did really well, people would take those specific values of those parameters and they would make them available on the internet for anybody to download. So if you download that, you don't just have an architecture now, you have a trained model. You have a model that can recognize 1,000 categories of thing in images, which probably isn't very useful unless you happen to want something that recognizes those exact 1,000 categories of thing. But it turns out you can you can start with those weights in your model and then train some more epochs on your data, and you'll end up with a far, far more accurate model than you would if you didn't start with that pre-trained model. And we'll see why in just a moment, right? But this idea of transfer learning, it makes intuitive sense, right? ImageNet already has some cats and some dogs in it. And it's, it can say this is a cat and this is a dog, but you want to maybe do something that recognizes lots of breeds that aren't in ImageNet. Well, for it to be able to recognize cats versus dogs versus aeroplanes versus hammers, it has to understand things like, what does metal look like? What does fur look like? What do ears look like? So it can say like, oh, this breed of animal, this breed of dog has pointy ears. And oh, this thing is metal, so it can't be a dog. So all these kinds of concepts get implicitly learnt by a pre-trained model. So if you start with a pre-trained model, then you don't have to learn all these features from scratch. And so transfer learning is the single most important thing for being able to use less data and less compute and get better accuracy. So that's a key focus for the FastAI library and a key focus for this course.
There's a question. I am a bit confused on the differences between loss, error, and metric.
Loss, error, and metric. Sure. So error is just one kind of metric. So there's lots of different possible labels you could have. Let's say you're trying to create a model which could predict how old a cat or a dog is. So the metric you might use is, on average, how many years were you off by? So that would be a metric. On the other hand, if you're trying to predict whether this is a cat or a dog, your metric could be, what percentage of the time am I wrong? So that latter metric is called the error rate. Okay, so error is one particular metric. It's a thing that measures how well you're doing. And it's like, it should be the thing that you most care about. So you write a function or use one of FastAI's predefined ones, which measures how well you're doing. Loss is the thing that we talked about in lesson 1. So I'll give a quick summary, but go back to lesson 1 if you don't remember. Arthur Samuel talked about how a machine learning model needs some measure of performance, which we can look at when we adjust our parameters up or down. Does that measure of performance get better or worse? And as I mentioned earlier, some metrics possibly won't change at all if you move the parameters up and down just a little bit. So they can't be used for this purpose of adjusting the parameters to find a better measure of performance. So quite often we need to use a different function. We call this the loss function. The loss function is the measure of performance that the algorithm uses to try to make the parameters better. And it's something which should kind of track pretty closely to the metric you care about. But it's something which, as you change the parameters a bit, the loss should always change a bit. And so there's a lot of hand waving there because we need to look at some of the math of how that works, and we'll be doing that in the next couple of lessons. Thanks for the great questions. Okay, so fine-tuning is a particular transfer learning technique where
Oh, and you're still showing your picture and not the slides.
So fine-tuning is a transfer learning technique where the weights, this is not quite the right word, we should say the parameters, where the parameters of a pre-trained model are updated by training for additional epochs, using a different task to that used for pre-training. So pre-training, the task might have been ImageNet classification, and then our different task might be recognizing cats versus dogs. So the way, by default, FastAI does fine-tuning is that we use one epoch, which remember is one, looking at every image in the data set once, one epoch to fit just those parts of the model necessary to get the particular part of the model that's specially for your data set working. And then we use as many epochs as you ask for to fit the whole model. And so this is more for those people who might be a bit more advanced. We'll see exactly how this works later on in the lessons. So why does transfer learning work, and why does it work so well? The best way, in my opinion, to look at this is to see this paper by Zeiler and Fergus, who were actually 2012 ImageNet winners. And interestingly, their key insights came from their ability to visualize what's going on inside a model. And so visualization very often turns out to be super important to getting great results. What they were able to do was they looked, remember I told you like a ResNet 34 has 34 layers? They looked at something called AlexNet, which was the previous winner of the competition, which only had 7 layers. At the time, that was considered huge. And so they took this 7-layer model and they said, what does the first layer of parameters look like? And they figured it out how to draw a picture of them, right? And so the first layer had lots and lots of features, but here are 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. And here's what 9 of those features look like. One of them was something that could recognize diagonal lines from top left to bottom right. One of them could find diagonal lines from bottom left to top right. One of them could find gradients that went from the top of orange to the bottom of blue. Some of them were able, one of them was specifically for finding things that were green, and so forth, right? So for each of these 9, they're called filters or features. So then something really interesting they did was they looked at for each one of these filters, each one of these features, and we'll learn kind of mathematically about what these actually mean in the coming lessons. But for now, let's just recognize them as saying, oh, there's something that looks at diagonal lines and something that looks at gradients. And they found in the actual images in ImageNet specific examples of parts of photos that match that filter. So for this top left filter, here are 9 actual patches of real photos that match that filter. And as you can see, they're all diagonal lines. And so here's for the green one, here's parts of actual photos that match the green one. So layer 1 is super, super simple. And one of the interesting things to note here is that something that can recognize gradients and patches of color and lines is likely to be useful for lots of other tasks as well, not just ImageNet. So you can kind of see how something that can do this might also be good at many, many other computer vision tasks as well. This is layer 2. Layer 2 takes the features of layer 1 and combines them. So it can not just find edges, but can find corners, or repeating curving patterns, or semicircles, or full circles. And so you can see, for example, here's it's kind of hard to exactly visualize these layers after layer 1. You kind of have to show examples of what the filters look like. But here you can see examples of parts of photos that this layer 2 circular filter has activated on. And as you can see, it's found things with circles. So interestingly, this one, which is this kind of blotchy gradient, seems to be very good at finding sunsets. And this repeating vertical pattern is very good at finding like curtains and wheat fields and stuff. So the further we get, layer 3 then gets to combine all the kinds of features in layer 2. And remember, we're only seeing here 12 of the features, but actually there's probably hundreds of them. I don't remember exactly in AlexNet, but there's lots. But by the time we get to layer 3, by combining features from layer 2, it already has something which is finding text. So this is a feature which can find bits of image that contain text. It's already got something which can find repeating geometric patterns. And you see, this is not just like a matching specific pixel patterns. This is like a semantic concept. It can find repeating circles or repeating squares or repeating hexagons, right? So it's really like computing. It's not just matching a template. And remember, we know that neural networks can solve any possible computable function, so it can certainly do that. So layer 4 gets to combine all the filters from layer 3 any way it wants, and so by layer 4 we have something that can find dog faces, for instance. So you can kind of see how each layer we get like multiplicatively more sophisticated features. And so that's why these deep neural networks can be so incredibly powerful. It's also why transfer learning can work so well, because like if we wanted something that can find books, and I don't think there's a book category in ImageNet, well, it's actually already got something that can find text as an earlier filter, which I guess it must be using to find, maybe there's a category for library or something, or a bookshelf. So when you use transfer learning, you can take advantage of all of these pre-learnt features to find things that are just combinations of these or existing features. And that's why transfer learning can be done so much more quickly and so much less data than traditional approaches. One important thing to realize then is that these techniques for computer vision are not just good at recognizing photos. There's all kinds of things you can turn into pictures. For example, these are sounds that have been turned into pictures by representing their frequencies over time. And it turns out that if you convert a sound into these kinds of pictures, you can get basically state-of-the-art results at sound detection just by using the exact same ResNet learner that we've already seen.
I wanted to highlight that it's 9:45, so if you want to take a break soon.
A really cool example from, I think this is our very first year of running FastAI. One of our students created pictures. They worked at Splunk in anti-fraud, and they created pictures of users moving their mouse. And if I remember correctly, as they moved their mouse, he basically drew a picture of where the mouse moved, and the color depended on how fast they moved, and these circular blobs is where they clicked the left or the right mouse button. And at Splunk, they then, what he did actually for the course as a project for the course is he tried to see whether he could use these pictures with exactly the same approach we saw in lesson 1 to create an anti-fraud model. And it worked so well that Splunk ended up patenting a new product based on this technique. And you can actually check it out. There's a blog post about it on the internet where they describe this breakthrough anti-fraud approach, which literally came from one of our really amazing and brilliant and creative students after lesson 1 of the course. Another cool example of this is looking at different viruses and again, turning them into pictures. And you can kind of see how they've got here, this is from a paper, check out the book for the citation. They've got 3 examples of a particular virus called vb.at and another example of a particular virus called Facrian. And you can see in each case, the pictures all look kind of similar. And that's why, again, they can get state-of-the-art results in virus detection by turning the kind of program signatures into pictures and putting it through image recognition. So in the book, you'll find a list of all of the terms, all of the most important terms we've seen so far and what they mean. I'm not going to read through them, but I want you to, please, because these are the these are the terms that we're going to be using from now on, and you've got to know what they mean. Because if you don't, you're going to be really confused, because I'll be talking about labels and architectures and models and parameters, and they have very specific exact meanings, and I'll be using those exact meanings. So please review this. So to remind you, this is where we got to. We ended up with Arthur Samuel's overall approach, and we replaced his terms with our terms. So we have an architecture which contains parameters as inputs, and parameters and the data as inputs. So that the architecture plus the parameters are the model. With the inputs, they're used to calculate predictions. They are compared to the labels with a loss function, and that loss function is used to update the parameters many, many times to make them better and better until the loss gets nice and super low. So this is the end of chapter 1 of the book. It's really important to look at the questionnaire, because the questionnaire is the thing where you can check whether you have taken away from this book, of this chapter, the stuff that we hope you have. So go through it, and anything that you're not sure about, the answer is in the text. So just go back to earlier in the book, and you will in the chapter, and you will find the answers. There's also a further research section after each questionnaire. For the first couple of chapters, they're actually pretty simple. Hopefully they're pretty fun and interesting. They're things where to answer the question, it's not enough to just look in the chapter. You actually have to go and do your own thinking and experimenting and Googling and so forth. In later chapters, some of these further research things are pretty significant projects that might take a few days or even weeks. And so, yeah, check them out, because hopefully they'll be a great way to expand your understanding of the material. So something that Sylvain points out in the book is that if you really want to make the most of this, then after each chapter, please take the time to experiment with your own project and with the notebooks we provide, and then see if you can redo the notebooks on a new data set. Perhaps for chapter 1 that might be a bit hard, because we haven't really shown how to change things, but for chapter 2, which we're going to start next, you'll absolutely be able to do that. Okay, so let's take a 5-minute break, and we'll come back at 9:55 San Francisco time.
Oh.
Okay, so welcome back everybody, and I think we've got a couple of questions to start with. So Rachel, please take it away.
Sure. First, are filters independent? By that, I mean if filters are pre-trained, might they become less good in detecting features of previous images when fine-tuned?
Oh, that is a great question. So assuming I understand the question correctly, if you start with, say, an ImageNet model, and then you fine-tune it on dogs versus cats for a few epochs, and you get something that's very good at recognizing dogs versus cats, it's going to be much less good as an ImageNet model after that. So it's not going to be very good at recognizing aeroplanes or hammers or whatever. This is called catastrophic forgetting in the literature. The idea that as you see more images about different things to what you saw earlier, that you start to forget what the things you saw earlier are. So if you want to fine-tune something which is good at a new task but also continues to be good at the previous task, you need to keep putting in examples of the previous task as well.
And what are the differences between parameters and hyperparameters? If I am feeding an image of a dog as an input and then changing the hyperparameters of batch size in the model, what would be an example of a parameter?
So the parameters are the things that are described in lesson 1 that Arthur Samuel described as being the things which change what the model does, what the architecture does. So we start with this infinitely flexible function, a thing called a neural network that can do anything at all. And the way you get it to do one thing versus another thing is by changing its parameters. They are the numbers that you pass into that function. So there's 2 types of numbers you pass into the function. There's the numbers that represent your input, like the pixels of your dog, and there's the numbers that represent the learnt parameters. So in the example of something that's not a neural net, but like a checkers playing program, like Arthur Samuel might have used back in the early 60s and late 50s, those parameters may have been things like if there is a opportunity to take a piece versus an opportunity to get to the end of a board, how much more value should I consider one versus the other? You know, it's twice as important or it's 3 times as important. That 2 versus 3, that would be an example of a parameter. In a neural network, parameters are a much more abstract concept, and so a detailed understanding of what they are will come in the next lesson or two. But it's the same basic idea. They're the numbers which change what the model does to be something that recognizes malignant tumors versus cats versus dogs versus colorizes black and white pictures. Whereas the hyperparameter is the choices about what numbers do you pass to the function when you the actual fitting function to decide how that fitting process happens.
Great. There's a question. I'm curious about the pacing of this course. I'm concerned that all the material may not be covered.
Depends what you mean by all the material. We certainly won't cover everything in the world. So yeah, we'll cover what we can. We'll cover what we can in 7 lessons. We're certainly not covering the whole book, if that's what you're wondering. The whole book will be covered in either 2 or 3 courses. In the past, it's generally been 2 courses to cover about the amount of stuff in the book. But we'll see how it goes because the book's pretty big, 500 pages. So.
And when you say 2 courses, you mean 14 lessons?
14, yeah. So it'll be like 14 or 21 lessons to get through the whole book. Although having said that, by the end of the first lesson, hopefully there'll be kind of like enough momentum and understanding that the reading the book independently will be more useful, and you'll have also kind of gained a community of folks on the forums that you can hang out with and ask questions of and so forth. So in the second part of the course, we're going to be talking about putting stuff in production. So to do that, we need to understand like what are the capabilities and limitations of deep learning. What are the kinds of projects that even make sense to try to put in production? And you know, one of the key things I should mention in the book and in this course is that the first 2 or 3 lessons and chapters, there's a lot of stuff which is designed not just for coders, but for everybody. There's lots of information about like what are the practical things you need to know to make deep learning work. And so one of the things you need to know is like, well, what's deep learning actually good at the moment? So I'll summarize what the book says about this, but there are the kind of 4 key areas that we have as applications in fast AI: computer vision, text, tabular, and what I've called here RecSys. This stands for recommendation systems, and specifically a technique called collaborative filtering, which we briefly saw last week.
Sorry, another question. Are there any pre-trained weights available other than the ones from ImageNet that we can use? If yes, when should we use others and when ImageNet?
Oh, that's a really great question. So yes, there are a lot of pre-trained models. And one way to find them...
But also you're currently just showing...
Yeah, I'm just switching them.
Okay, great.
And one great way to find them is you can look up Model Zoo, which is a common name for like places that have lots of different models. And so here's lots of model zoos. Or you can look for pre-trained models. And so, yeah, there's quite a few. Unfortunately, not as wide a variety as I would like. Most are still on ImageNet or similar kinds of general photos. For example, medical imaging, there's hardly any. There's a lot of opportunities for people to create domain-specific pre-trained models. It's still an area that's really underdone because not enough people are working on transfer learning. Okay, so as I was mentioning, we've kind of got these 4 applications that we've talked about a bit. And deep learning is pretty good at all of those. Tabular data, like spreadsheets and database tables, is an area where deep learning is not always the best choice, but it's particularly good for things involving high cardinality variables. That means variables that have like lots and lots of discrete levels, like zip code or product ID or something like that. Deep learning is really pretty great for those in particular. For text, it's pretty great at things like classification and translation. It's actually terrible for conversation. And so that's been something that's been a huge disappointment for a lot of companies. They tried to create these like conversation bots, but actually deep learning isn't good at providing accurate information. It's good at providing things that sound accurate and sound compelling, but we don't really have great ways yet of actually making sure it's correct. One big issue for recommendation systems, collaborative filtering, is that deep learning is focused on making predictions, which don't necessarily actually mean creating useful recommendations. We'll see what that means in a moment. Deep learning is also good at multimodal. That means things where you've got multiple different types of data. So you might have some tabular data, including a text column and an image, and some collaborative filtering data. And combining that all together is something that deep learning is really good at. So for example, putting captions on photos is something which deep learning is pretty good at, although again, it's not very good at being accurate. So it might say this is a picture of 2 birds when it's actually a picture of 3 birds. And then this other category, there's lots and lots of things that you can do with deep learning by being creative about the use of these kinds of other application-based approaches. For example, an approach that we developed for natural language processing called ULM-FIT that we'll be learning in the course. It turns out that it's also fantastic at doing protein analysis. If you think of the different proteins as being different words, and they're in a sequence which has some kind of state and meaning, it turns out that ULM-FIT works really well for protein analysis. So often it's about kind of being creative. So to decide, like, for the product that you're trying to build, is deep learning going to work well for it? In the end, you kind of just have to try it and see. But if you do a search, hopefully you can find examples of other people that have tried something similar. Even if you can't, that doesn't mean it's not going to work. So for example, I mentioned the collaborative filtering issue where a recommendation and a prediction are not necessarily the same thing. You can see this on Amazon, for example, quite often. So I bought a Terry Pratchett book. And then Amazon tried for months to get me to buy more Terry Pratchett books. Now that must be because their predictive model said that people who bought one particular Terry Pratchett book are likely to also buy other Terry Pratchett books. But from the point of view of like, well, is this going to change my buying behavior? Probably not, right? Like if I liked that book, I already know I like that author, and I already know that like they probably wrote other things, so I'll go and buy it anyway. So this would be an example of like Amazon probably not being very smart here. They're actually showing me collaborative filtering predictions rather than actually figuring out how to optimize a recommendation. So an optimized recommendation would be something more like your local human bookseller might do, where they might say, oh, you like Terry Pratchett? Well, let me tell you about other kind of comedy, fantasy, sci-fi writers on the similar vein who you might not have heard about before. So the difference between recommendations and predictions is super important. So I wanted to talk about a really important issue around interpreting models. And for a case study for this, I thought let's pick something that's actually super important right now, which is a model in this paper. One of the things we're going to try and do in this course is learn how to read papers. So here's a paper which I would love for everybody to read, called High Temperature and High Humidity Reduce the Transmission of COVID-19. Now this is a very important issue because if the claim of this paper is true, then that would mean that this is going to be a seasonal disease, and if this is a seasonal disease, then it's going to have massive policy implications. So let's try and find out how this was modeled and understand how to interpret this model. So this is a key picture from the paper. And what they've done here is they've taken 100 cities in China, and they've plotted the temperature on one axis in Celsius and R on the other axis, where R is a measure of transmissibility. It says for each person that has this disease, how many people on average will they infect. So if R is under 1, then the disease will not spread. If R is higher than like 2, it's going to spread incredibly quickly. And basically R is going to, any high R is going to create an exponential transmission impact. And you can see in this case, they have plotted a best fit line through here. And then they've made a claim that there's some particular relationship in terms of a formula, that R is 1.99 minus 0.023 times temperature. So a very obvious concern I would have looking at this picture is that this might just be random. Maybe there's no relationship at all, but just if you picked 100 cities at random, perhaps they would sometimes show this level of relationship. So one simple way to kind of see that would be to actually do it in a spreadsheet. So here is a spreadsheet where what I did was I kind of eyeballed this data and I guessed about what is the mean degrees centigrade. I think it's about 5. And what's about the standard deviation of centigrade? I think it's probably about 5 as well. And then I did the same thing for R. I think the mean R looks like it's about 1.9 to me, and it looks like the standard deviation of R is probably about 0.5. So what I then did was I just jumped over here and I created a random normal value. So a random value from a normal distribution, so a bell curve, with that particular mean and standard deviation of temperature, and that particular mean and standard deviation of R. And so this would be an example of a city that might be in this data set of 100 cities, something with 9 degrees Celsius and an R of 1.1. So that would be 9 degrees Celsius and an R of 1.1. So something about here. And so then I just copied that formula down 100 times. So here are 100 cities that could be in China, right? Where this is assuming that there is no relationship between temperature and R, right? They're just random numbers. And so each time I recalculate that, so if I hit Control equals, it will just recalculate it, right? I get different numbers, okay, because they're random. And so you can see at the top here, I've then got the average of all of the temperatures and the average of all of the R's, and the average of all of the temperatures varies, and the average of all of the R's varies as well. So then what I did was I copied those random numbers over here. Let's actually do it. So I'll go copy these 100 random numbers and paste them here, 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 here. And so now I've got 1, 2, 3, 4, 5, 6. I've got 6 kind of groups of 100 cities, right? And so let's stop those from randomly changing anymore by just fixing them in stone there. Okay, so now that I've pasted them in, I've got 6 examples of what 100 cities might look like if there was no relationship at all between temperature and R. And I've got their mean temperature and R in each of those 6 examples. And what I've done is, you can see here, at least for the first one, is I've plotted it, right? And you can see in this case there's actually a slight positive slope. And I've actually calculated the slope for each just by using the slope function.